Last time, we talked about imaginary numbers and using imaginary numbers as a way of encoding oscillation into the exponential solution of an ordinary differential equation. But most systems do not just oscillate forever. They typically experience decaying oscillation due to damping. For instance, this slinky oscillates in gravity. But how should we adapt the exponential solution so that a spring mass damper system like this one can decay? Let's look at our model of the spring mass damper again. Again, we have the wall on the left, a spring, a damper, and a mass at the end. The equations of motion are x double dot is equal to minus k over m x minus b over m x dot. And we're going to assume that the solution is of the form of an exponential function. That is, that x of t is equal to e to the ht times w, where w is just a constant. If we plug this solution into the differential equation above, and keeping in mind it is in second order form with two time derivatives of x of t, we get h squared e to the ht times w is equal to minus k over m e to the ht times w minus h times b over m e to the ht all times w. We can factor out the e to the ht term as well as the constant w, and we get h squared plus b over m h plus k over m all times e to the ht w, and that all must be equal to 0. If w is non-zero, and we know that the exponential is always non-zero, then we know that h squared plus b over m h plus k over m must be equal to 0. Hopefully you recognize that this is in quadratic form, so we can use the quadratic formula, which says that if we have three coefficients, alpha, beta, and gamma, then alpha h squared plus beta times h plus gamma equal to 0 implies that h is equal to negative beta plus or minus the square root of beta squared minus 4 alpha gamma, all of that divided by 2 alpha. In our specific case, the quadratic formula tells us that h is equal to minus b over m plus or minus the square root of b squared over m squared minus 4 times k over m. All of that divided by 2. This means that the h in the exponential solution is a solution to the quadratic formula. Note that the plus or minus sign means that there will be two solutions, one that corresponds to the plus sign and one that corresponds to the minus sign. If b is equal to 0, that is, there is no damper in the system, this simplifies to something we have seen before. That is, b equals 0 implies that h is equal to plus or minus square root of k over m times j. This is the same solution that we found last time, so we know it will give us sine and cosine terms and that the system will oscillate forever. However, if b is non-zero, then something else can happen. Let's set k equal to 1 and m equal to 1. Then we get h is equal to minus b plus or minus the square root of b squared minus 4 all over 2. If b is greater than or equal to 2, then h has no imaginary values because the term in the square root is positive. When h does not have an imaginary number, the system is called overdamped because it will not experience any oscillation at all. If b is less than 2, then h will have imaginary values because the term in the square root is negative. When h does have an imaginary component, the system is called underdamped. For instance, if b is equal to 3, that implies that h is equal to minus 3 plus or minus the square root of 5 all over 2. And so I get two values, neither of which involve the imaginary number j. This will give me an exponential solution of the form x of t is equal to e to the minus 3 plus square root of 5 over 2 t all times w, or e to the minus 3 minus the square root of 5 over 2 times t, all times w. If I instead choose b equal to 1, then I'll get a different type of solution. What we'll see is b equal to 1 implies that h is equal to minus 1 plus or minus the square root of negative 3 all over 2. Now, with that, I get two solutions. x1 of t is equal to e to the minus 1/2 plus or minus the square root of 3 over 2 times j, all times t times w. Now, here, I'm going to only choose the plus version. And now my second solution becomes x2 of t is equal to e to the minus 1/2 minus the square root of 3 over 2 j, all times t and times w. Now remember from calculus that e to the r plus s is equal to e to the r, e to the s. And what this implies is e to the minus 1/2 plus the square root of 3 over 2 j times t, all times w. That's equal to e to the minus 1/2 t times e to the square root of 3 over 2 j times t, all times w. So I can separate the terms that involve the imaginary number j from the terms that do not. For instance, now I can take this term right here and point out that it's equal to the cosine of square root of 3 over 2 times t plus j times the sine square root of 3 over 2 times t. Using the same trick as last time to get rid of j, we can conclude that solutions are of the form of an exponential times cosine and sine terms. To visualize this, a plot of e to the minus 1/2 t times cosine of the square root of 3 over 2t is helpful to look at. In particular, the exponential term, its plot looks something like this, while the cosine term looks something like that. Together, they would look like a decaying oscillation. So what should you remember from today? Remember that exponential solutions can both represent oscillation and decaying oscillation.